Hi, I'm Alvaro Calafell, and this third video is the second part about harmonics and their origin. In the last video, we explained the origin of harmonic currents, and in the present video, we will talk about the harmonic voltages. We should remember that the origin of harmonic currents are the nonlinear loads which consume periodic but non-sinusoidal currents. These currents can be decomposed in several sinusoidal currents of different frequencies. The current of the same frequency as the original one is the fundamental frequency, while the other sinusoidal waveforms are the harmonics, which are introduced in the network by nonlinear loads. According to this, we will now see four examples of non-sinusoidal currents consumed by nonlinear loads. Up to the left, we have the non-sinusoidal current consumed by discharge lamps, the waveform in red, and the non-sinusoidal current consumed by LED lamps is the one in orange. Down to the left, we have the typical current consumed by single-phase rectifiers, and on the right, we have the typical current consumed by three-phase rectifiers. To study harmonic voltages, we can imagine that we have a sinusoidal supply voltage which feeds a nonlinear and a linear load in the following circuit. The nonlinear load consumes a periodic but non-sinusoidal current. Nevertheless, the voltage at the load terminals remains sinusoidal, because this voltage is equal to the supply voltage, so it seems that harmonic voltages are not produced by the harmonic currents injected by the nonlinear loads. This is not exactly true. In fact, the harmonic voltages are produced by the presence of nonlinear loads and other network components, so these harmonic voltages are not produced exclusively by harmonic currents injected by the nonlinear loads. To understand this, we will analyze the following situation. Here we have the same circuit as the previous one, but this time the impedance of the grid is included, where we have a voltage drop. In this situation, the voltage at the load terminals is equal to the sinusoidal supply voltage, minus the voltage drop at the grid impedance. This voltage drop is the impedance times the distorted current consumed by the nonlinear load, plus the sinusoidal current consumed by the linear load. As this current is distorted, the voltage drop is also distorted, and the voltage at the load terminals result distorted with harmonics. In conclusion, even if there were nonlinear loads in the circuit, there will be no harmonic voltages when the grid has no impedance. On the other hand, the voltages become harmonically distorted when there are nonlinear loads injecting harmonic currents through the impedances of the grid. We can conclude that the origin of harmonic voltages is the presence of harmonic currents injected by nonlinear loads and the impedance of the grid. This means that the harmonic voltages depends on two factors, the root mean square value of the harmonic currents and the value of the grid impedance. If one of them is high, large values of harmonic voltages will appear, and these voltages become highly distorted. For example, the value of the impedance depends on the frequency. If we have a peak value of the impedance at one of the frequencies of the harmonic currents injected by the nonlinear loads, we could have an harmonic problem with the voltages. An example of a sinusoidal supply voltage which feeds through the impedance of the grid 10 single-phase rectifiers of 2 kW each can be seen below. Each one consumes a non-sinusoidal current from the following graph. The voltage at the nonlinear load terminals becomes non-sinusoidal due to the distorted currents consumed by the nonlinear loads and the impedance of the grid. It can be seen as the load voltage presents a flat zone instead of the peak value of the sinusoidal supply voltage. This flat zone matches with the peak of the current consumed by the single-phase rectifiers. The tables show the characteristics of the current and the voltage waveforms, that are the root mean square value of the current and the phase angle for each harmonic of the current and the voltage. To complete these videos about harmonics and their origins, I am going to provide you with a script in MATLAB code to determine the harmonics of our periodic but non-sinusoidal waveform. Remember that any periodic but non-sinusoidal waveform can be decomposed in a summatory of a sinusoidal waveform characterized by the root mean square value and their phase angle at each harmonic. First, the program reads the data of the waveforms and puts time and waveform values in two vectors. After that, it calls the MATLAB function of the Fourier transform and takes out the harmonics from the vector provided by the MATLAB function. Subsequently, the program determines the root mean square value and the phase angle of each harmonic and builds a summatory of the sinusoidal functions recovering the original function. At last, the program compares in a plot the original and the recovered waveforms.